Hello and welcome back. Today I'm going to continue talking about operational amplifiers, and in particular the input and output limitations. And to start things off, let's talk about the voltage follower circuit. Classical OpAmp circuit in which the output should be exactly the same as the input, and this is achieved by having an amplifier gain of 1. So exactly what goes in must come out. Now to show this circuit, I've prepared here 3 identical circuits in which the difference is the OpAmp. So I'm looking at 3 OpAmps, and if I run the simulation, you may notice that I changed a bit my display window. Hope this improves things. And this is our input signal, and for the first OpAmp, the output is exactly the same. Just like we expected from the typical voltage follower circuit. Now if we look at the LM741 typical OpAmp, with the exact same circuit, the output, this red one, doesn't really look as sine wave-ish as it should. So we got our top and bottom pieces cut off. And if we look at the LM324 or 2902 or whatever, they're all the same, just different, just the same. Again, we have a different sort of output. So our upper part is chopped off, but our lower part is unaffected. So what's going on? I mean, are the simulation models wrong? Well, no, they're models taken from the various manufacturers' websites, so simulation models are right. Actually, this is a perfectly normal behavior, and if you're curious about why this is happening, how to identify this in the datasheet, and what are the constructive limitations that each of these op-amps have that give rise to this sort of behavior, then keep watching. So before anything else, let's identify these limitations in the datasheet. We can start by looking at the 741 operational amplifier. Now if we scroll down through this, we'll find some of its parameters here in the datasheet. Now what I'm interested in today is first of all the input voltage range. Now this parameter tells us what are the voltages acceptable on the inputs of the op-amp, so the inverting and non-inverting inputs. And these are specified for a differential supply of plus minus 15 volts. So if we supply this op-amp at plus minus 15 volts, then our input voltage range will be a typical plus minus 13. So we have a 2 volt limitation on the input, 2 volts from the supply rails. But in extreme cases it can be up to 3 volts. So this is a problem with the input stage of the op-amp. Now if we look at some of the other op-amps that I've just simulated, for example the LMX24X and many other things, so they're all bunched together. If we look for the exact same parameters, we no longer have the parameter defined as input voltage range, but rather a common mode input voltage range. Now by common mode you can understand that this refers to the average voltage of the two inputs. But since when you're using the op-amp the two input voltages are roughly exactly the same, then you can consider this the exact same parameter as the input voltage range. It's just defined a bit differently. Now for this op-amp we have somewhat different values. Whereas before it was defined as a voltage difference from both supply rails, so 2 volts from the positive, 2 volts from the negative. For this op-amp we can see that from the ground there's 0 offset, so you can go directly to the negative voltage, whatever it is, but you have a limitation from your positive voltage. So we can see that it's the positive voltage minus 1.5 volts on the input. And if we consider the full temperature range, then it will be 2 volts. So again, this is a problem of the input stage, so we'll be looking at that in a moment. But just from these values we can work out that the input stage of this op-amp is slightly different than the one we previously looked at. So let's see what's causing these problems. Let's look at some input stages, see how they're built. So this is the classical operational amplifier input stage, the comparator. So what I got here is 2 input sine waves, which are slightly shifted. I'm supplying the circuit from 5 volts, and then I've got my circuit built right here. So the 2 inputs, the 2 transistors, a resistor on the emitter, and then 2 resistors on the collectors. And to see the output of the op-amp, I've placed this resistor in between the 2 collectors, and depending on the direction of the current through this resistor, we will say that one voltage or the other is higher. So let's see this circuit in action. Let's first of all look at our 2 input signals. We've got 2 sine waves, same frequency, just slightly shifted, so that the difference will never be very great between the two. So half the time the blue line is the highest voltage, half the time the green line is the highest voltage. Now if we look at the current through this common collector resistor, we can see that when the green line, so the positive input, is higher, then the current is positive, so it's above 0 microamps. When the blue line is the highest voltage, then the current is negative, so the current flows the other way through the resistor. Now the first thing you may notice is that if you actually compare the two input voltages, always one of the voltages is higher than the other, except for very small amounts of time when the two voltages overlap. But in practice, the output of the OpAmp has these flat areas, which are quite wide. So for a certain amount of time, when both voltages are approaching the 5V supply limit of the circuit, the comparator output flattens out, and the same thing is happening when the two voltages approach the negative supply line, so at 0V. Again, the output of the comparator is flattening out. Now, to understand where our input voltage range limitations that we have in our datasheet are coming from, we need to understand where these flat areas are coming from, since these will explain our input stage limitations. So let's take them one step at a time. First of all, let's look at the low voltages, when our input voltages are very low. So with this stage, we've got a problem. This lower resistor. Because it's a resistor, the current going through the comparator stage varies. So it's a nice sine wave. This is completely unacceptable if you want a proper OpAmp input stage. And normally this is replaced with a proper current sink so that your comparator operation is a bit more stable. So we'll be analyzing this circuit in which the resistor has been replaced with a current sink to better understand what is going on. So here again we have the same behavior. We've got the output current of the comparator flattening out when the two voltages are low. So what's going on when the two voltages are low? Well, to be able to drive the comparator, we need to be able to drive the transistors in the comparator. So let's look at these two transistors down below. To drive transistor Q8, we are supplying it from our positive supply, 5V, never changing, everything is fine, no problem with it. To drive Q7, we've got signal from the same line, so we don't really have any problems with it, or any limitations. Now we do have a limitation in the collector emitter voltage. Depending on the type of transistor, this needs to be above or around 0.1, 0.2 volts, since that is the collector emitter saturation voltage. So the lowest voltage you can get in this point is around 0.1, 0.2 volts. Now if we look at the transistors in the comparator itself, we know that between the base and emitter we have the PN junction. So if we actually want to drive any of these two transistors, we need to have the base voltage higher than the emitter voltage by around 0.5, 0.6 volts, which is added on top of the voltage drop on our lower transistor. So in total, if we actually want to compare two voltages, we need to drive the two transistors and the one on the bottom, so the minimum voltage between our inputs and the ground needs to be around 0.7 volts. You cannot use this sort of input stage with input voltages lower than 0.7 because of this. Now, what happens if we go to very high input voltages? The base emitter voltage always stays roughly the same, so if we have 5 volts on the input, then the emitter will be roughly 0.6 volts below that, so 4.4, not a problem. The low transistor can handle this without any issue, so it can sink currents through it at voltages even higher than 4.4, at 5, at 6, at 10, doesn't matter. So our high voltage limitation is not coming from these three transistors. The high voltage limitations comes from something else. When we're driving any sort of OpAmp, we want the input current to be 0. Now if we look at the input current through this stage, we'll see that it's roughly 0 until it's not 0 anymore, until it jumps up to 3 point something milliamps. Now that is completely unacceptable for an OpAmp. So what's going on? Well, our low side current sink has a current threshold of around 4.4 milliamps, which normally is drawn through these upper resistors, either the one on the left or the one on the right, depending on which of the two input voltages is the highest. Now if our input voltage goes to very high voltages, let's say 5 volts, as we said, the emitter needs to be roughly 0.6 volts below that, so 4.4. Now the collector emitter voltage on a transistor can have high voltages, so it can go up to 10, 20 depending on the transistor, but the minimum is the saturation voltage, which is, as we said, around 0.1, 0.2. So if we have 4.4 in the emitter plus 0.2, that's 4.6. That means that on our high side resistor, we've got 5 volts minus the 4.6, 0.4 volts. Now, we can do a quick calculation on that. So if we divide 0.4 volts by 1 kilo ohm, that means that we can get only 400 microamps. Nowhere near the 4 milliamps that we actually need to drive our circuit. So if our input voltages are very high, then the current through the comparator will no longer be going through the collectors of the two transistors, it will be going through the emitters. That's exactly what we are seeing here. When one of the two input voltages is very high, then the current is starting to get drawn through the bases of the inputs. It's no longer coming through the collector. Depending on which voltage was highest, the current will be coming from that side. So our high voltage limitation comes from the upper part of the comparator stage. Now in proper op-amps, this again has been replaced, so you no longer find these resistors, you find a current mirror. What this does is that it gives us a much flatter response. So in this case, the output is from the right side transistor. That means when our positive input is the highest, then our output will be a flat, high voltage response. Now this stage still suffers from the same problem. So if we look at the currents through the base, we still have these spikes. And this is the sort of input stage that we find in our LM741 op-amp. We've got our two inputs, we've got some current sinks, and there's all sorts of voltage drops on all of these transistors. And by looking at all of these, you will end up with the input limitations that you've got in the datasheet. So let's move on. How can we get at least one of our inputs to go to a certain rail? Well, we can use this sort of input stage. So what makes this different from the previous one? Well, we've got a small difference. We've got two transistors on either input. This means that if we have on one of the inputs the supply voltage, so 5 volts, we've got on the emitter of the first transistor minus 0.6, so 4.4. On the emitter of the second transistor, again minus 0.6, so 3.8. And then in the emitter of this transistor, we've got 3.8 plus 0.2, so 4 volts. That means that this time we have a whole volt to spare on our high side input stage. Therefore we can ensure much higher currents through these resistors. And the circuit will work a bit better. So we still have this problem, the current flattening out when the input voltages are very high. But again, if we replace these resistors with a current mirror, our output will be much more clear. So we will have a proper response when our input voltages are very high. So this sort of input stage will not work at low voltages, it will be even worse because of the two junctions this time, but it will work much better at high voltages. And this is exactly the sort of stage we have in our LM324 op-amp. Now, it has been inverted, so these are PNP transistors on the input, not NPN as in my simulation, but we got the double input transistors on the two input stages, we've got our current mirror and the constant current supply. Now, there's one more thing to discuss. In my initial simulation, I had one op-amp whose input was exactly the same as the output. So what's going on here? Why don't we have any limitations, neither on the top side, neither on the bottom side? I mean, we saw why we have limitations and how to improve them on one of the extremes, but not on both. Well, this is actually done by doing this sort of input stage twice. And we get to this op-amp, so there's many like it, but this is just one example, but this is part of a class of rail-to-rail op-amps. Now rail-to-rail means it goes with its parameters to both of the supply rails. If we look in the datasheet to the input voltage range, we can see that this can go to minus 0.3 below the supply voltage, up to 0.3 above the positive supply voltage. So it cannot just work with the voltage range of the supply rails, but it can go to a bit above and a bit below. And now they are not giving us a properly detailed input stage, but we can see how this was achieved. Basically, you've got an input stage with N-channel transistors and an input stage with P-channel transistors. So one of these stages can go to the top supply rail, one of these stages can work with the bottom supply rail, and then you just combine the output of the two stages and use that to drive your operational amplifier. So basically, the rail-to-rail input stage is achieved by combining two input stages that can go to either of the rails. And the total circuit obtained at the end can go to both supply rails. And these are the main types of input stages, and these are the input limitations. Now there's one more input limitation I would like to discuss today before moving on to the output limitations, and to better illustrate this, I will be looking at the OP27 OpAmp. Now this is quite a good OpAmp. It has the typical input limitations of almost 3 to 4 volts, so when you're supplying it with 15 volts plus minus, then your input voltage range can be as low as plus minus 11, so from that point of view it's not very great, but that's not what I want to talk to you about. What I want to talk to you about is this absolute maximum rating, the differential input voltage. What this means is what is the permissible voltage difference between the two inputs. Now with the previous op-amps, we didn't really have this limitation, so the differential input voltage for the 741 was plus minus 30 volts, so this is the two extreme supply voltages. But for this op-amp it's tiny, 0.7. So what's going on? Well, if we have a closer look at the input stage, we will see that we have these protection diodes between the two inputs. And if you drive the difference between the two inputs to more than 0.7 volts, then you will destroy these diodes, leading to the destruction of the op-amp. Now, why would you bother putting these diodes in? I mean, aren't they just a bother? Well, these things have a very good purpose. First of all, if the difference between your two inputs is very large, then you're not really using the op-amp as an op-amp, you're using it as a comparator. So you don't really need a proper op-amp for that. Secondly, these input stage transistors are highly sensitive. Now, in general for a transistor, the collector-emitter voltage can be quite high, in the order of dozens of volts or even hundreds. But your base emitter voltage, the forward bias one is 0.7, but the reverse bias one is always a small voltage. It's in the order of a few volts. Now for op-amps, since these transistors are tiny and with high precision, the reverse bias voltage is very small, especially in such more specialized circuits. So these diodes are put here not just to keep the op-amp in an op-amp mode of operation, but also to protect these input transistors. So when you're designing a circuit with an op-amp and you're choosing the op-amp for that circuit, one of the things to also consider, apart from the input voltage range, will be the differential input voltage, so that you don't exceed any threshold, if any. Okay, so let's move on. Just like with the input stage, we've got certain parameters in the datasheet characterizing the output stage. Now there's quite a lot of parameters, but what I want to go into today is talk about the output voltage swing. So just like we talked about what are the voltages that can appear on the input, I want to discuss the voltages that can occur on the output of the op-amp, so the output voltage swing. Now for the 741 op-amp, for a supply voltage of plus minus 15 volts, we've got two values here in our typical category. So we got an output range of plus minus 14 when the load is higher than 10 kilo ohms, and plus minus 13 when we're talking about smaller loads, so somewhere between 2 and 10 kilo ohms. So again, we've got a certain voltage limitation from each of the two supply rails, either 1 or 2 volts. Now if we look at a different op-amp, so the LM324, this parameter is no longer defined as the output voltage swing, but rather is defined as two different parameters: the high level output voltage and the low level output voltage. Basically, these two parameters tells us what's the highest value the output can take and what's the lowest value. It's defined as two different parameters since it's no longer a symmetrical behavior. So we can see that our high voltage, depending on the load, can be 2 volts away from the supply rail or more than 2 volts. So the minimum for loads of 2 kilo ohms can be 4 volts away from the supply rail. This is in the case of the supply taking a maximum value, which is defined here below as 30 volts. Now the low level output voltage for loads smaller than 10 kilo ohms is defined as being 5 millivolts. So very low voltages, which are very close to the supply rail, can be taken on the low level output, but on the high level output we have a certain limitation, so of a few volts. And if we look at the last op-amp we've analyzed today, the OPA 342, which is the rail-to-rail type of op-amp, we see that in this case the output can go very close to either of the two rails. So this time it's defined as a symmetrical value, which depending on the output load can be as low as 1 millivolt or as high as 400 millivolts for the defined load of 5 kilo ohms. So what's going on? What makes these three amplifiers so different one from the other? Well, let's have a look at how the output stages can be built in typical operational amplifiers. So this is the typical Class AB output stage. Now if we simulate this, so for the purposes of this exercise, I'm just giving it a simple input signal, so going from one extreme to the other, just so we can see the output voltage range. And even with absolutely no load connected to it in an ideal environment in a simulation, we can see that the output voltage has a certain limitation on the low side. So we got 600 millivolts as a minimum output voltage, and for some reason around 5 volts as a high output voltage, so exactly the same as the supply rail. Now, of course, in reality you will never use this op-amp without a load. You will always use it connected to a certain resistive load. Now if we look at this sort of output, then we will see that we have nice limitations both on the upper side and on the lower side. So why can't this stage go from one rail to the other? Why does it have this 0.6 volt limitation both on top and on the bottom? Well, again, it comes down to how the stage is built. If you want a certain voltage on the output, you need to get that voltage through one of the transistors, either the high side or the low side. If we want to drive the high side transistor, we need to be able to have a voltage in the base higher than the voltage on the emitter by around 0.6 volts, so the PN junction. The maximum voltage that we can get in the base through this resistor is the supply voltage, so 5 volts in our case. So no matter what load we put on the output, as long as it's a defined load, the base voltage can go as high as the supply voltage, but the emitter will always stay 0.6 volts lower than that, therefore giving rise to this 4.4 volt maximum limit if we supply it with 5 volts. The exact same thing is happening on the low side transistor. So if we drive the base of this PMP transistor to ground, so the minimum voltage at which the stage is supplied, then the emitter will always be 0.6 volts higher than the base, giving rise to this low voltage limitation. Now in more complicated output stages, which have been designed to handle much higher currents, for example this thing, so we've got Darlington transistors both on the high side and on the low side, our output limitation will be even worse. So this time we're no longer having to drive only one PN junction, but two PN junctions, both on the high side and on the low side. And with this sort of output stage, we've got a symmetrical limitation of around 1.2 volts. Again, depending on how well the circuit is designed and built. Now we can have symmetrical limitations and we can have asymmetrical limitations. For example, with this stage. Here we've got the 0.6 volt low side and the 1 volt high side limitation, even though we are using double transistors both on top and on the bottom. That's because on one side we've got two NPNs, on the other we've got a PMP and an NPN. So depending on how you're designing your output stage, you will have various limitations. So this is nice. We can see where we get our limitations. So how do we get rid of these limitations? Well, the simplest way of getting rid of either one of the limitations or both is to use this sort of output stage, the Class A output, in which we have a low side transistor and on the high side we've got a constant current source. In this case, our output will go from one rail to the other. No limitations, only given by whatever saturation voltage we got on either of the transistors. So with this sort of stage, although highly inefficient, we can get a rail-to-rail type of operation. So why is that? Well, if we drive our low side transistor with any sort of signal, we will have in the base 0.6 volts more than the emitter, but on the output of the op-amp, the only limitation is coming from the collector emitter saturation voltage. Same thing is happening on the high side. We've got a constant current source, the current is being set using the transistor and resistor on the left side, which drives the base of the high side transistor, but the collector emitter voltage drop again has a minimum value of the saturation voltage. Now, as I said, this is a class A type of output, which is inefficient. So there will always be current going through this stage. You cannot turn it off. Now, of course, you can make more complicated circuits, which are not shown in the OPA datasheet, to control this sort of transistor output stage in the class AB type of regime. But one way of combining the two output stages, so the class AB and the class A, can be seen in the LM324. Here, if we look at the output stage, we can see the typical class B. So the high side transistor is an NPN with the emitter pointing to the output. The low side is a PNP with the emitter again collected to the output. So how does this OpAmp manage to get the output as low as a few millivolts, as we've just seen in the datasheet? So they're saying that although it's a B class, they get 5 millivolts on the output low level. Well, this is possible because of this, a 50 microamp current regulator. Or in other words, up to 50 microamps, this is a class A type of output stage. We've got a constant current sink on the low side, but on the high side we always have this sort of transistor arrangement. So for very low currents we can go with the output voltage to the negative supply rail, but with the high output swing we are limited by these two transistors. And of course, when much higher currents are needed, then this 50 microamp current regulator steps out and it becomes a proper class B type of output stage. And there would be one more thing to mention. We have seen that the output voltage is defined for different loads with different values. So why isn't the voltage the same for any sort of load? Well, this comes from the gain of the transistors and from any sort of protection circuitry built into the OpAmp's output. If this OpAmp would work with any currents, then it would most likely destroy itself. So after a certain current, the output stage will not be able to work. Likewise, if you're using a certain current, not exactly the one that is the limit, but also not zero either, the voltage drop on the various components will be dependent on the current. So for every PN junction, the voltage drop will be somewhere between 0.5 and 0.7 depending on the current. And on certain output stages like this one, we've got an overcurrent limit protection. So we've got this resistor in series with the high side output, and when the voltage drop on this is high enough, it will drive this transistor. So again, apart from the 0.7 plus 0.7, 1.4 volts drop on these two transistors, we will have an extra 0.7 volt drop on this transistor at the point at which the overcurrent limit kicks in. So depending on how the output stage is built, you will have various voltage drops which are current dependent. So all in all, when choosing an OpAmp for your circuit, depending on what you want to do with it, you will always need to take into consideration not just the input limitations, but also the output limitations. Just because you're supplying the OpAmp with a certain voltage doesn't mean that the OpAmp can actually handle that voltage on the inputs and the outputs. This will be especially important when designing circuits with very low supply voltages. And that's about it from me for today. So, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with my latest videos. And hope to see you next time. Bye bye.